next speaker is Ivan Tomasic. He's going to be speaking about a Topos theoretic view of difference algebra.
Thank you very much. I'd like to thank the organizers for the opportunity to speak. And I'd like to present to you possibly a slightly new way of looking at difference algebra. And I hope by the end of this talk to convince you that it's beneficial to do it this way. So I'll start by revising. In fact, Michael in his talk already revised the kind of classical Ritt-style difference algebra. I'll maybe just mention how you might want to categorize this difference algebra. And then I will talk about the topos of different sets. And it's not necessary to understand what a topos is from a technical perspective, but somehow I would like you just to think of it. A topos is some kind of category which is as good as sets in the sense that you can consider them as universes for building mathematics inside. And then after discussing that, I will show how to actually give some applications of this approach and present an approach to developing difference homological algebra, and then what I consider is a kind of solid foundation for difference algebraic geometry. So, as it was already mentioned, difference algebra is classically considered as the study of rings and modules and possibly other algebraic structures with added endomorphisms. So you superimpose the operators on top of classical structures. Now, if you want to build some categories this way, this is how you do it. You start with some category C, and then you want to define a difference category out of this C. So you say the objects are pairs consisting of an object of the old category together with an endomorphism. And then a morphism between two such objects is just a commutative diagram in the old category. In other words, it's a morphism which commutes with difference operators. So that's the usual notion. Now, the typical examples that will appear throughout this talk will be different sets. So those are just sets with self-maps. Difference groups, so that would be groups with homomorphisms. And difference abelian groups or difference rings. And then once you fix a difference ring, you can consider the category of difference R modules. And you'll notice, which probably annoys many people, that I don't indicate. So when I say R, this is a difference ring. I don't indicate that it has sigma R on it. Yeah, so that's kind of included in the structure. So, all right. Now, let's discuss our universe. First of all, we build a rather small category. So sigma underline is the category associated to the monoid n plus, to the additive monoid of natural numbers. It has a single object, O, and then homomorphisms of O to itself are isomorphic to the monoid n. And then different sets can be viewed as the functor category, or in other words, the category of sheaves, of pre-sheaves on this small category sigma underline, and that makes it a Grothendieck topos. So the definition of a Grothendieck topos is that it is a category of sheaves on some site, and so this is a very trivial example. The literature also calls this object the classifying topos of n, and it's written Bn, and that's just a category of sets with an action of n. I hope you can see that this is equivalent to saying that this is different sets, because the action of n is actually encoded by the action of 1, of the element 1. Okay, that's the difference operator. So these are several ways of viewing different sets. I probably use another 5 ways, but I'm not going to bother you with these other descriptions of different sets. But the important thing is that it is a topos, and that it's going to be suitable for developing mathematics inside. All right. Now, I want to name some important functors. So, given that these are kind of pre-sheaves, they have global sections. Now, the global sections actually correspond to just taking fixed points. So if you take the different set, you can consider the set of fixed points, and not just a set. So you get a functor from different sets to sets. And then another notable functor is the forgetful functor from different sets to sets, where you just omit the difference operator. Okay, so topos theory has this philosophy that any topos is good enough to serve as a universe for developing mathematics, which I already said a couple of times. Now, what makes topos so good? Well, you have products, you have some co-products in there. You can talk about sub-objects. You have certain objects which encode logic, truth values, and also you can talk about characteristic functions of sub-objects. And you can talk about power sets, power objects, etc., etc. So these are all kind of virtues that are suitable for kind of developing most of mathematics. And our motto becomes that difference algebra is best viewed as the study of algebraic objects internal in the topos of different sets. And the method of working is that you use the internal logic of this new universe, and you pretend to be doing ordinary mathematics. And then when you externalize, so there's a technical construction of externalization, that actually gives you some new fancy objects that actually are going on. So, but somehow the point is that we're going to do ordinary mathematics, but in a new universe. Now, indeed, difference groups are just group objects in this category. Okay? So a group object is just an object together with the object G, together with the morphism G cross G to G, which is multiplication, and so on. But if this G is already a different set, that means that the multiplication commutes with difference operators. So this is, difference groups are simply speaking groups in the universe of sigma sets. Similarly, difference rings are just ring objects in the category of sigma sets. And now for modules. So if you take a difference ring, then the pair difference sets and R becomes a ringed topos. So this is a standard thing to consider. And then when you consider modules for this ringed topos, you're actually getting the category of difference R modules. Now, these observations are completely trivial, and you might ask, okay, so why are you telling us about this? You haven't told us anything new. However, I'm going to soon illustrate that basically, even though, these are trivial observations, thinking internally in different sets will quickly produce some new objects that possibly haven't been considered before. Okay? So let's look at the internal Hom construction. So the problem that we're trying to address here is that when you take two different sets and you consider the set of all maps between them, the set of all difference maps between them, those maps that commute with sigmas, this is not a sigma set. But we placed ourselves into a new universe. Everything has to be a sigma set. So you can't talk about the usual Hom. You have to create an internal Hom, some construction which will play a role of morphisms, but will live inside your universe. Okay, so that's internal Hom. And this is how we construct it. So internal Hom between two different sets can be obtained either by looking at the usual sigma sets of natural numbers cross x to y, and noting that this actually has an action of +1 in n, which makes it a different set. Or my preferred way is to consider these internal Homs as sequences of ordinary maps which don't commute exactly with sigmas, but they commute up to a shift. Yeah? So, and then this shift is what makes this internal Hom a different set. Okay? And the benefits of this is that it makes the category of different sets into a Cartesian closed category, which means that you have this currying isomorphism. So, which for sets, this is a trivial thing. And for sets, it works even if you just put Hom yz here. But for different sets, you will notice that if you try to put just the usual sigma set Hom here, this is just a set, and this thing doesn't make sense at all. And it's even if you could somehow furnish the usual Hom with some artificial difference operator, it's way, way too small to make this hold. Okay, but this is important, and you'll see that, okay, the relationship to the usual Hom is that the fixed points of the internal Hom give you the usual Hom. So Ritt-style difference algebra only sees a small bit of what's actually happening in the background. The way to justify this relation is if we go back to the diagram. You see, if one of these tuples is fixed by the shift, that means that all the fi's are equal, which just means that you have commutation on the nodes. Right? So, okay, now that's not so kind of impressive for sets, but the point is that you can fix the Hom tensor duality for difference modules in the same way. So, if you take difference R modules over a difference ring R, the Hom set is not a difference R module. It's at best module over the fixed ring. So, however, when we produce an internal Hom, which is basically the same construction as previously with these ladders, except every step in the ladder is classical module homomorphism, then this internal Hom actually becomes R module, difference R module. And you have Hom tensor duality like this, which desperately fails, as I already said, desperately fails if you try the usual difference Hom here. So, that immediately gives you some hope that now you can develop difference homological algebra, because homological algebra rests on a number of basic duality properties like this. Okay, so we can start doing things. Right, now it's a fact that when you take any Rotany topos and a ring object in that Rotany topos, then the category of modules has enough injectives. It's a GR5 abelian category, and you can perform, you can calculate derived functors, and you can develop a homology theory. So, because we're viewing these different R modules as modules of a ringed topos, we know that this is automatically satisfying. And the cohomology of difference modules is just a special case. It's an instance of the usual Topos cohomology. So for two difference modules, you can talk about X functors, you can talk about cohomology, and so on and so forth. So if you remember that morphism from different sets to sets, gamma lower star was just the fixed points. So in fact, the cohomology is just deriving the fixed point functor. So let me show you some calculations. If you take a difference ring and then two R modules, where the first one is Étale, and that means for me that the sigma twist of F is isomorphic to F. Then you can compute the X functors very explicitly in terms of the internal hom. So, okay, the zeroth one, nothing happens. It's just the hom of F prime. In the first degree, you get the, okay, so this is the internal hom. Now, internal hom has a shift, and this is co-invariance for the shift. Okay? And then it vanishes above degree 1. Now, if I didn't assume that F is Étale, I couldn't get this, but the theory of cohomological dimension of skew polynomial rings gives you that you have vanishing above 2. So with I like this special case. It's a much nicer result. Now that in particular applies to deriving to calculating derived functors of fix. And okay, so the zeroth is just the fixed functor, fixed point. The first derived functor is sigma coinvariance of the module, and then they vanish above degree 1. So we're going to use this later on.
Was that because R itself was Étale?
Yeah, exactly. All right. So, given our general philosophy, we proclaim that for us, difference algebraic geometry is algebraic geometry over the base topos sigma set. And a colleague of mine pointed out that there exists this monograph of Monique Hakim, who was a student of Grothendieck, who basically just wrote a thesis, which became a monograph, and then stopped working in that area. But it's a brilliant thing. So it develops algebraic geometry over a base topos, and that's the approach we use. And we're going to unravel what it gives when you take the base topos different sets. So, okay, so when you have a ringed topos, it just means that A is a ring object in a topos epsilon. You can construct the Zariski spectrum of that, which is a locally ringed topos which has a kind of morphism of ringed topoid to the original one, and this solves a certain two-universal problem. It's like some kind of universal localization of the original ring. You know, without changing the topos, you cannot find a universal localization of a ring. You have to go to a bigger topos to do that. Now, when epsilon, for example, when you would take epsilon to be just sets and A is an ordinary ring, then this is related to the classical spectrum. However, okay, the usual spectrum is a ringed space. And here we're looking for a ringed topos. So this will actually give you the topos of Zariski sheaves on the spectrum of A. Okay? So in the classical case where E is sets, spec Zar is the category of Zariski sheaves on spec A. All right. Now, however, I mean, Hakim goes further. For any kind of reasonable scheme topology of your choice, be it Zariski or Étale or flat, or whatever, you can define the tau spectrum as well. Okay, so our goal is to define that the affine difference scheme associated to a difference ring A is Hakim's Zariski spectrum. And then if we, for example, want to work with a tau or flat site, then we're going to use this tau spectrum of that Zariski spectrum. Okay? And let's see what I promised to Michael that I would give the details of what this actually gives. So let's try. I mean, it's a bit technical, so, but let's try. Okay. So let us denote by S tau the classical tau site of the spectrum of the underlying ring. Right. So this thing is just the ordinary ring, and we know what the spectrum of that is. And we know what is a tau site. So this is just schemes over spec A, and the coverages are defined by topology tau. Or if you want to work with a small site, you then further restrict. Okay. So the tau spectrum of the underlying ring will be the sheaves on this site S tau. So that's the classical side of the story. Okay, now, however, if A is a difference ring, then this site admits the base change functor along sigma A. So that gives you kind of endo functor on this category ST. And you see the pair of a category with an endo functor is an internal category in the topos of different sets. So it's kind of like a category object inside that new universe. And okay, you can also define topology on it to make it into an internal site. And then the tau spectrum is the topos of internal sheaves denoted this way. So if you're not used to internal category theory, this is tricky to grasp, but I can unravel what this actually gives. So these, the morale of internal sheaves is, sheaves are usually, sheaves on a usual site are set values. Here, these are kind of meant to be difference set values. Yeah? So anyway, we have a more explicit description following. So Étale is in fact the category of sigma equivariant sheaves on the underlying classical topos. So these are those sheaves on the classical tau in the classical tau topos, which are equipped with a morphism from F to F composed the base change. And all right, there's a natural geometric morphism going from this tau topos to different sets, which should be thought of as the global sections functor. And then you can recover the difference ring as just the global sections of the structure sheaf. So, in difference algebra, there have been many various approaches to, how to define a difference scheme. And at some point, when one considers the fixed point scheme, the problem is that you cannot recover the original ring. But I think this relative picture, where you take this Zariski spectrum and look at it over the topos of sigma sets, that is like a perfect analogy. Okay, so I hope this is the final definition. All right, so how to now define cohomology of? Are there any questions? All right, so how do we define cohomology of difference schemes with intention that there should be an instance of the usual topos cohomology? We don't want to invent anything new because we want to tap into the existing literature, which is vast. Okay, so anything from Grothendieck's SGA or anything from the Stacks project, which is formulated in the generality of ringed toposes, will apply. Okay? So when you have a tau spectrum, it has a bunch of these geometric morphisms. So this is the one I mentioned previously, which is like the relative global sections functor. Then this is the taking the fixed points that I already mentioned, and then this is the composite. Okay, so if you now take M, which is an OT module, or simply an abelian group in there, you can define the absolute tau cohomology and relative tau cohomology groups in the following way. So the absolute cohomology of M is simply computing the derived direct images by this composite. Okay, so you get abelian groups. It lands in sets, so the outcome of this is abelian groups. And the relative cohomology is taking higher direct images alongside this functor here, and that actually lands in sigma sets, so you're getting difference abelian groups. All right. So if you're interested in just getting some cohomology group, you do this. If you want a difference group, which has an action of sigma, you do this. Now, because this functor is the composite of these two, of course you have Grothendieck spectral sequence to connect them. So Grothendieck-Leray spectral sequence comparing the relative and absolute cohomology degenerates into exact sequences. Now, so why is that? Because we proved earlier that the derived functors of the fixed point functor vanish above 1, So out of the entire spectral sequence, you have like a narrow band, which is basically just breaks down into a bunch of exact sequences like this. So you have
that applies for scheme as well as for different string.
so this
I
is
think the earlier was
yeah. So
for a ring.
But okay. The earlier work was for this part. So gamma lower star is the fixed point functor. So we've done this part. We resolved this part. And now we're talking about taking the composite of these two, and we're using the Grothendieck spectral sequence to calculate the cohomology of this using the information about this and that.
But now if I think a projective variety, then the gamma is trapped with direct images.
This is the variety.
Yeah.
Yeah.
But now, for map gamma,
Gamma is always there.
take a projective variety with an endomorphism.
Yeah. So that's
And
here.
it's still trapped in that.
That's here. I mean,
Yeah.
gamma is always this one, just this one. This part of the picture does not change. Any new variety goes in here. This x is the variety that you're working with. Yeah. So this part of the picture is always the same. Yeah. And this is where the fix happens. And yeah. So anyway, so this is the kind of lower degree relative cohomology. These are difference abelian groups. So you can take sigma co-invariants, and this is, say you want to calculate this guy, and so it's sandwiched between the previous degree cohomology co-invariance and invariance of its degree, relative cohomology. We also have a comparison of the relative cohomology groups to cohomology of the underlying scheme, which is very simple, but the reason why we still want to think of this as the relative cohomology is that it's much more natural to consider, and certain objects have a much more beautiful description. So this, this thing has an action of sigma, but it's much more transparent when you think of it this way. Okay, so now with this machinery, we can now start working and do some actual calculations. So, okay, classifying torsors using cohomology group H1. So this is a completely general theory. So it works in an arbitrary ring topos, therefore applies here. So if G is an abelian group in X tau, so it's most interesting when tau is the flat topology, then the torsors are classified by H1 of G up to isomorphism. So the category of torsors is a groupoid. By tors 1, I denote the associated group of isomorphism classes. And so there are connections there to the work of Annette and Michael and Chalupnik-Kowalski, which is a recent paper. And they identify completely independently a number of objects that I just talked about. All right. Now, something that I haven't seen done before. So, as I said, the category of torsors is a groupoid, but it's just an ordinary groupoid. However, by thinking that we live in the new universe, we can't really talk about ordinary groupoids. It has to be a difference groupoid. So we define the difference groupoid of some kind of internal or generalized G torsors I omit the definition, but it's in my paper, if you're interested. And they are actually classified by the relative cohomology, H1. Okay. So this is already contained in Hakim's monograph, this result, on cohomology of quasi-coherent sheaves. So if you take a difference ring and look at the corresponding affine scheme, and then you take an A module and consider the associated module, OX module to that, then in classical algebraic geometry you have vanishing theorems for cohomology of such modules, and you have them here as well. Okay, but this is already proved by Hakim in full generality for an arbitrary ground topos. It doesn't need to be different sets. Okay, so you also have Hilbert's theorem 90, which says that if you take a different scheme and then you look at the sheaf corresponding, Étale sheaf corresponding to the multiplicative group, then calculating H1 for Étale cohomology gives you the same as H1, there's a 1 missing, H1 for flat cohomology, or H1 for Zariski cohomology. And this has a natural interpretation of the Picard group, which is just a group of invertible sheaves on your scheme. And yeah, don't worry, later I'll give. So, you know, very few people would recognize Hilbert 90 from this picture. Usually it's for a field. I'll give a calculation for a field. So, all right, yeah, all these usual exact sequences simply work. So if n is invertible in a different scheme X, you have a short exact sequence. So these are, I don't know why I put n here, it should be m. So these are multiplicative groups, and this is raising to the nth power, and mu n is kind of the sheaf of roots of unity, which is simply the kernel of this. The difficult question is whether this is actually onto. And when you work on the Étale side, it is onto. And basically boils down to explaining that, when you want to show that this is onto, you're considering somehow nth roots, and you have the polynomial t to the n minus a, and you need to say that this is a separable polynomial. Okay, so Kummer theory actually refers to considering the corresponding long exact cohomology sequence to this. And then also, in a similar way, you have Artin-Schreier theory, where you consider this structure sheaf for the Étale side, and you look at the map associated to f to the p minus f. And so, yeah, so all of these things work, and you can then, it's interesting to write out the full long homology sequence and spot which terms you can work out, and then the unknown terms are somehow sandwiched in between the ones that you can work out. So for difference fields, when you do that for a difference field, you get that, so H1 with respect to the multiplicative group, Étale fundamental group of K is, as we already noted by Hilbert 90, is the Picard group, but it's simply the multiplicative group of the field and then sigma coinvariance of that. And you can get that the kind of H2 with respect to GM which is meant to be like the difference Brouwer group, is obtained in a very straightforward way from the Brouwer group of the underlying field as simply as invariance, sigma invariance of that. Now, if you kind of try to work out the Étale cohomology of K with respect to these roots of unity coefficients, you get some kind of interesting and mysterious short exact sequences like this. So what do they mean? Okay, so this is the multiplicative group of the field. Then you take sigma invariance, and then you take co-kernel of taking the nth powers. Whereas here you have sigma coinvariance of the multiplicative group, and then taking the kernel of raising to the nth power. And similarly, the other one. Okay, so I promised in the abstract to mostly speak about homology, but in fact I want to illustrate the whole program. So we can also talk about difference Galois theory, not in the sense that usually discussed in this conference, but in the sense that you want to describe the fundamental group of these different schemes. And the difficulties that have to be overcome are quite, prohibitive, I would say, because you see, in classical Grothendieck-Galois theory, you can always assume that the base scheme is connected. If the base scheme is not connected, you just say, okay, take connected components and then focus on considering one of those. But here, the examples from Michael's talk where you have infinite product of rings with a shift, that can give you a different scheme which is topologically totally disconnected, something like a Cantor set, and yet sigma permutes the components wildly, and it's indecomposable. You cannot simplify it any further. Also, such a scheme may not have field theoretic difference field points. So, usually for the fundamental group you fix a base point, but you may not have a base point. And also, so the base Topos sigma set is not Boolean. If you study lots of proofs in Grothendieck's Galois theory, they depend on being able to take complements, and the fact that the double complement is the original object in the category of sets. But sigma sets is not a Boolean Topos, so you have all sorts of difficulties. But okay, we can work with that. There are two things that you can use, and then hopefully they will compare. And Janelidz's categorical Galois theory has been used by Andy for differential case, so we propose to do it for difference case, and you get some kind of difference version of his separable Galois theory of commutative rings. And so this is very good because it can work with really horribly disconnected base. However, there's some drawbacks. Now, this is the picture that I like more. There's this relative Galois theory, which has been pursued mostly by Bunge and then maybe Moerdijk, which when you have a locally connected morphism of topoi, you can obtain a localic fundamental group in the base topos. So that's going to be like a topological group in sigma sets, which is associated to this situation. Now, when, the only problem is when this morphism is locally connected. If you take a really horrible base scheme, then it's not. However, when it is, we can compare the two and get a really beautiful, well-integrated theory. So by the way, for difference fields, it does agree with what we consider to be the right, Michael and I, which is basically the absolute Galois group of the underlying field with the sigma twist. So you get the shape of the theory is that you're getting a difference group acting on difference sets. All right. So I'd like to just advertise the poster of my PhD student Antonino here. So his goal is to go through everything I just said in the differential case. Now, what is going to be the approach? So William Geiger, unfortunately, is not here today, but he was here yesterday. He developed a notion of differential algebra in an arbitrary topos E. And certain important constructions of free differential ring, etc., etc. And our idea is that different differential rings can be considered as differential rings in the topos of different sets. And then you use some of this, and Antonino's task is to emulate kind of homological algebra the way I've done, the way I've showed you slightly earlier. And you can see some more details in his poster. And I'd like to kind of conclude with the advert for the program, like why pursue this program. And I say Ariadne's thread. So topos theory gives you this thread that you can follow. Usually, the biggest predicament of a researcher in difference algebra is what is a suitable analog? So what is a suitable difference analog of some classical result or some classical object? With this approach, or with this following this program, you don't have to think. It's just given to you. Okay? You just have to work out. You just have to work out what it is. Also, the program is quite general. We happen to work over the base topos Bn, classifying topos of the monoid of n plus. But you can replace this with an arbitrary monoid or group or category and obtain the corresponding equivariant geometry. So, having said what I said in number 1, it isn't an easy job. So, working out what topos theory gives you, even in the simple case of a topos like different set, is actually quite hard. And it took me through the majority of the chapters of Johnston's Sketches of the Elephant, which I didn't intend to do when I started on this. However, it just naturally takes you almost, and it's I think the 2 volumes are a bit maybe like that. So thank you very much for your attention.
Are there any questions? So you mentioned externalizing. What is the injectives in the category for difference modules look like as modules? In particular, do you know anything about their homological properties and modules?
Yeah. So basically, results of the existence of enough injectives and so on are obtained by using certain free constructions and these geometric morphisms between the topoids. So you're going to use an injective from the usual sense, and then apply some kind of free construction to it. So like an infinite product of copies of this thing with some shift. So yeah, I mean it's not that we care precisely what they are, but in certain cases, especially under this assumption of sigma tau modules, I was able to write some explicit short resolutions, for some special modules. So, yeah, this, I mean, injectives are difficult to understand anyway. But in this case, they're built from injectives, the classical injectives in the category of sets, and then you apply some free constructions to them.
So there was, a few years ago, there was a lot of interest among geometers about the effect of either morphism, Euclidean variety, or some kind of projective variety. And it sounds like this is a setting that allows you to analyze exactly that kind of thing. I'm not going to ask if you've ever thought about it. I know it's very hard to do computations, but it seems like a natural.
So okay, I think so. This setup is sort of it's a kind of God's gift for doing cohomology and homological algebra, but I wouldn't think that it can match the results obtained by model theorists, through stability theory, like in Khrushchevsky's proofs of Manning-Mumford, where he used classification of definable sets for difference fields, or the kind of recent O-minimality results, which are used for kind of Andrew conjecture. So I think this setup is really good for calculating some cohomology groups, but I think I don't think it can prove Diophantine statements in number theory.
So
Yeah, I don't know.
I have a related question to Becky. So in the classical context, right, if you want to study a module or representation of differential algebra, you can convert that to the study of usual modules or representation of real differential operators.
Yes.
So how does that work in this context? The conversion.
I mean, this is a point of view. So for example, those results I was giving on homological algebra of just these kind of results. People, difference module is just a module over a skew polynomial ring, but then this becomes a non-commutative ring. But people studied those things, and there are results. They know that, for example, they have cohomological dimension 2, and so on and so forth. So, but for example, okay, this result is with this additional assumption, but you cannot get such sharp results there. I don't think you can. So it's of course it's a valid point of view, and you have to bear it in mind. But somehow, this is just in addition, and it's interesting that this internal hump kind of appears in this calculation, and possibly I mean I haven't had the chance to speak to an expert on skew polynomial rings, but this could be a new result, maybe, I don't know. But I mean, there are many experts on difference algebra, and you know, I always wanted to ask, you know, has anyone seen internal homes being used, you know, previously? I think I searched through your books, and I think there is a mention of internal home, but for in the differential book. Yeah. Where it's just the usual home with an induced derivation. But
Any other questions?